Happy to have Tony Pantev from UPenn, who will speak about enhanced moduli of D-branes and superpotential. So I ask everyone except of Tony to mute their audio. Okay.
Okay. Well, thank you. So, all right. So I'm going to talk about a story in symplectic geometry on derived spaces or derived stacks. But what the ultimate goal really is about, it's about understanding structures on moduli spaces and understanding actually a dichotomy that exists in modeling parameter spaces of objects in mathematics and in physics, and so there is some kind of a disconnect between the two approaches to modeling parameter spaces, and what this story is about is to try to connect them. So I mean, I'm gonna briefly review. So first of all, yeah, it's based on a bunch of works. Some of them are written, some of them are still being written, with Damien Calaque, Katzarkov, Bertrand Toen, Gabriele Vezzosi, and Toen Vaquie. And I'm gonna start with a quick review of symplectic geometry in the context of derived algebraic geometry. So it's this notion of a shifted symplectic geometry. And then I'll try to explain how it connects with the notion of a foliation. And then I'll talk about the structure theorems, which are the Derived theorems, and show you how they can actually produce for you the extra structure then that on moduli spaces that you expect to have from external or physics considerations. So I'll do some examples. All right, so let me say something about the symplectic structures. So if you have a, so these are all, you know, for people who are, haven't heard this before, haven't seen it before, these are all algebraic symplectic structures. So everything is happening in the world of algebraic geometry. And for concreteness, I'm going to do complex algebraic geometry. So if you have a smooth complex algebraic variety, which I'm calling X here, a symplectic structure is what you are normally used to calling a symplectic structure. So it's a closed algebraic two form, which happens to be non-degenerate. So it has the property that when you contract with it, the tangent vectors, you get cotangent vectors, and this contraction map is an isomorphism between tangent and cotangent. So this is what a symplectic structure is. And those guys, they are natural extra structures that you actually get on solutions to moduli problems in algebraic geometry. So when you look at interesting moduli problems in algebraic geometry, very often you get these symplectic structures from some internal consideration on the moduli problem, either from the deformation theory or from some additional algebraic structure on cohomology or something like that. So these solutions to moduli problems in algebraic geometry, they carry a lot of extra information, which appears in terms encoded in some type of algebraic structure. And when you try to reinterpret this extra information in terms of geometry, you usually end up either with symplectic structures or some kind of metric structure. And so these symplectic structures, they naturally come on solutions to moduli problems. The problem is that solutions to moduli problems tend to be singular. So if you want to understand how these symplectic structures manifest themselves in the general situation when you actually have singularities, then or you have some other fuzz in the moduli problem. Say you have stackiness, something like extra automorphism groups attached to points, or you have some first in the function theory. So your function theory has nilpotents, which is something that very commonly happens in algebraic geometry, especially for solutions of moduli problems. Or more generally, you have nilpotents that sit in different homological degrees. So all of these are additional kind of decorations that you get on algebraic varieties, or especially algebraic varieties that come as solutions to moduli problems. And you would like to understand how these symplectic structures interact with them. So you understand what a symplectic structure is on the smooth locus, but you would like to understand what would it mean for that symplectic structure to be pushed to the singular locus, or to the locus where we have these extra automorphisms, or where we have these extra nilpotents in the function. And you immediately notice a couple of things. One is that the tangent bundle and the cotangent bundle, or the tangent sheaf and the cotangent sheaf, are too crude as invariants capturing the infinitesimal structure of your varieties, your singular or Stocky or derived spaces. If you really want to capture the infinitesimal structure, you need to actually redesign what you really mean by germs of curves, or what you mean by derivations, or what you mean by differentials. And at the end of the redesign, you actually, instead of a single sheaf or a single of tangent vectors, or a sheaf of one forms, you get actually a complex of tangent vectors and a complex of one forms. So that's the first thing that you need to come to grips with, that you need to modify if you want to understand these more complicated spaces. And the second, which again, I'm going to elaborate on that in a moment, is that the fact that once you understand what the infinitesimal theory is, the fact that the form is closed actually turns out not to be a condition in this case, but turns out to be extra structure. Because, you know, one forms already, they are like elements in a complex, so they're chains in a complex. And what it means for a form to be closed, either one form or a higher degree form, it would be something about having boundaries in that complex, which is intrinsic. It has nothing to do with the Derived differential. So both of those actually affect your notion of a symplectic structure, and I'm going to try to explain how. So let me give you some details about the tangent and the cotangent complexes that capture the infinitesimal structure of singular or Stocky or derived varieties, just so that we have something concrete in mind to work with. So suppose that we have X, which is not a variety, but maybe a singular variety, not a smooth variety, but maybe a singular variety, or maybe a stack, or maybe a stack equipped with these extra nilpotents in the function theory, so a derived stack, for which the function theory is actually differential graded algebra. And all the higher degrees in that differential graded algebra sitting in negative homological degrees. So you can ask, what is a tangent vector in this guy? And well, what is a point? A point is a map from the point to X, and a tangent vector is a map from a thickened point to X, so from the spectrum of the dual numbers to X. So this X guy is really now, so the points in X, because it's a singular guy or a derived guy or a Stocky guy, the points in X. So if you probe X by something affine that you understand, the collection of probes, the collection of points, is now not really a set, but it's in fact simplicial set. And so you can look at the points of your derived stack over the field C, or over the algebra of the dual numbers. So this is just polynomial ring modulo the variable square. And so this is the thickened point. And so now these are simplicial sets or topological spaces, and you have a map between them. And so the fiber of that map is again a simplicial set or topological space, is the homotopy fiber. And you can take the normalized chain complex associated with that simplicial set, and it's a simplicial abelian group. And that will, with that simplicial abelian group, by the dot-Kahn correspondence, you can associate the complex, and that's the tangent complex. So if the guy was smooth, that simplicial abelian group will just be a group, and the normalized complex will be just a vector space, or get the tangent space. But if we are with this extra fuzziness, then we have to really work with that complex. So you get a tangent complex, and this complex has actually geometric meaning. So if X was parameterizing some geometric objects, or algebraic objects, or analytic objects, or physical objects, then the tangent complex has terms in various degrees. Its -1 degree cohomology are just the automorphisms of the point, the object that the point represents. The degree 0 cohomology are the deformations, first order deformations of the object that the point represents. And the higher degree cohomology, they contain the obstructions to deformations, but they contain extra information too, because remember, our points actually are parameterized now by extra data. They are automorphisms, and then they are their functions. Yeah, was there a question? I wasn't sure if somebody tried to ask a question.
So far, everything is clear. Yes.
Okay. So let me just give you some specific examples. So if your X is just the quotient of a point by a group, so it looks like a point with one group of automorphisms attached to that point, which is an algebraic group G, then the tangent complex only has one stalk at the point, and it is just the Lie algebra of the group, but there is a difference. So it's just single vector space, but this vector space really doesn't sit, it's not a vector space because it sits in different homological degree. It sits in homological degree -1. That just because the group has disappeared, it only sits in those automorphisms. So they're no tangent vector proper, but they are tangent vectors to automorphisms which sit in homological degree -1. So the tangent complex really is a single term guy, but it sits in homological degree -1. Another example that you can easily visualize is if you take a manifold, say M, and you take two smooth submanifolds, L1 and L2 in it, and you intersect them. So if you take their intersection, that gives you a space, but that space actually has fuzz in the function theory, because if the intersection is not transversal, then the functions on one space and the functions on the other space, viewed as algebras over the functions of the ambient space, they will not interact in a locally free way. There will be relations in the interaction. So if you want to understand the function theory of the intersection, you need to take the tensor product of the two over the functions on the ambient space. But the tensor product will have cohomologies, will have to be derived, because these algebras as algebras over the functions on the ambient thing are not flat. And so when you look at that, these cohomologies will appear as pieces, nilpotent pieces in your function theory of the intersection that sit in different homological degrees. And so the tangent complex to the non-transverse intersection, it actually has two pieces. One is the sum of the tangent spaces to the guys we're intersecting, and the other is the tangent space to the ambient variety, and we will look at the map between them. So it's a complex that has two terms, one sitting in degree 0, the other sitting in degree 1, and the cohomology in degree 0 is just the tangent space, the Zariski tangent space to the intersection. But there is a cohomology in degree 1, which is the failure to transversality of the intersection. And so this tangent complex actually remembers both of them. And for instance, if you take X to be the moduli of vector bundles of a smooth projective variety, then the tangent complex is just the cochain algebra of the endomorphism bundle with a homological shift. The same thing works if you're doing local systems, locally constant sheaves on a compact manifold. It is the cochain algebra of the endomorphism local system with the homological shift 1. In a slightly more geometric example, if you look at maps from one smooth variety to another, C to Y, then the tangent complex to the moduli of maps at a given map is just the cochain algebra of the pullback of the tangent bundle of the target under the map. So these are all examples to show you that these tangent complexes that appear naturally, they're not wild. I mean, they're complicated, but they are something that is there, and it captures geometric information in any constructive situation. So they are really capturing the Foucault homology of a bundle or of a local system, or capture the non-transversality to intersection, things like that. So this is what tangent complexes are. And you can talk also about cotangent complexes. So if you have a commutative differential graded algebra, which we're thinking about the algebra of functions on some derived space, and the derived space is formally the spectrum of that algebra, then you can talk about one forms of that affine derived space by replacing the algebra by a nice algebra, by a semi-free replacement. So it's a commutative differential graded algebra, and it's always homotopy equivalent to a commutative differential graded algebra, which is semi-free, meaning the underlying algebra that you get without the differential, when you ignore the differential, is a free algebra or polynomial algebra on finitely many generators in each degree. So you can always replace some differential graded algebra by a cofibrant semi-free one like that, which is homotopy equivalent or quasi-isomorphic. And then the cotangent complex of your algebra is just the Keller differentials on this semi-free replacement. So it's a complex, it's not quite uniquely defined because it depends on the replacement, but it's well defined up to quasi-isomorphism. So if you take two different semi-free replacements, their Keller differentials are quasi-isomorphic. And then, you know, you can globalize this by saying that the sections, if you have a derived stack, then the sections of the cotangent complex on any affine open given by differential graded algebras are just the Keller differentials on a cofibrant replacement, and you just take the limit of that. So the cotangent complex is a complex of quasi-coherent sheaves on your derived stack. We say that X is locally a finite presentation, so that means that locally this algebra of functions, it's actually a polynomial algebra on finitely many variables, so maybe in different homological degrees, but totally finitely many. And this is, in this world of singular or derived or Stocky spaces, this is the analog of a smooth space. Because for these guys, for these types of algebras, the cotangent complex is actually perfect. It's a complex that's locally quasi-isomorphic to a complex of finitely many free modules or finitely many vector bundles. You know, this is like the analog of the usual notion of smoothness, where we say that a space is smooth or a variety is smooth if its Keller differentials are a vector bundle. So, which turns out that up to étal change of variables, it's the same as saying that locally it looks like a polynomial algebra. So this is the analog of being smooth in this world. And so the cotangent complex is perfect, so it's isomorphic locally to a complex of finitely many finite rank vector bundles. And in that case, it turns out that the duo of the cotangent complex, so the literal linear algebraic duo, is isomorphic to the tangent complex that we defined before by using germs of curves. So this is my review of the infinitesimal theory of stacks and derived spaces, and it also tells you what the smooth objects are in that world. They're the guys for which the cotangent complex or the tangent complex are not quite a single vector bundle, but are isomorphic locally to a complex of finitely many vector bundles. So for the purposes of doing differential theory, this is as good as having just a single vector bundle. Okay, and I don't know what happened. I wanted to get back here. So this is my discussion of tangent and cotangent complexes, and now I want to talk about what it means in this universe for forms to be closed. But maybe, are there any questions on the infinitesimal theory before I move on?
So is there in general any relation between tangent and cotangent, or you need, you mentioned that sometimes they can be just dual to each other.
Yeah, right. So if the guy is not smooth, there is a priori no relationship between them. And in fact, it could happen. So if you have a derived stack, which is not locally a finite presentation, you know, it's not locally given by function theory, which is essentially polynomial algebra, but maybe, you know, graded polynomial algebra, then there is no a priori relation between the tangent and the cotangent complex. I mean, there is a map from the dual to the cotangent complex to the tangent complex, but that map could be totally wild. In fact, it could happen then the cotangent complex does not exist in general. Because, you know, if your algebra, or it's trivial, it's contractible, if your algebra is not, you know, it has unbounded growth in generators, it could be that they're not Kähler differentials at all. So it could happen that your cotangent complex doesn't exist. But if it does exist, then there is a map from the dual of the cotangent complex to the tangent complex. But that map can be trivial or can be completely wild. I mean, may not have any information in it. So you really need your tangent and cotangent complexes to be of reasonable size. So being locally finite presentation is sufficient. So they are, you know, perfect complexes, and then they're actually dual to each other. There is something that you can do which is weaker than that. So there is this notion of Geitz-Gorey and Rosenblum of almost perfect function theories. So that means that the tangent and the cotangent complex is not perfect, but it's locally quasi-isomorphic to a complex of finitely many vector bundles, but possibly of infinite rank. And that actually is already good enough theory. So there is a lot you can say about the relationship between the tangent complex and the cotangent complex in this case. And that actually does appear in practice, especially when you work with formal schemes.
Yeah, but do you have in mind some not finitely presented complex, not just, you know, an example to illustrate the limitation, but since you have something like D-branes in the title, in the nature, some kind
no,
of...
so in the stuff that appears in nature, they're all perfect. So you don't need to worry about this this extra freedom or extra complicated situation. But you know, as you'll see in a moment when we talk about formal stacks, sometimes, when you're dealing with formal stacks, you really need to allow almost perfect guys. But if you formulate your moduli problems, so there is this hidden smoothness philosophy of Kuntsevich, which essentially says that any moduli problem which is intrinsically formulated as a derived moduli problem ends up being a locally finite presentation, so ends up having a perfect tangent complex. And so that you can actually prove theorems about that. You can prove that reasonable deformation theories always have this property and things like that. And in all the examples that we'll talk about with D-branes, that they will have this property, so we don't have to worry about that.
Okay.
So yeah, so let me talk about forms being closed. So if you have a smooth scheme, again, smooth variety over the complex numbers, you can talk about the closed P-forms, closed algebraic P-forms, the same way you do it in differential geometry, but with algebraic coefficients. But in fact, we know from Hodge theory, it's more fruitful, it's more useful to talk not about closed P-forms, but about a complex of forms that's essentially equal to the closed P-forms. It's quasi-isomorphic to the sheaf of closed P-forms. And that complex is the stupid truncation of the de Rham complex. So if you take the de Rham complex and you cut it at degree P, just look at omega P goes to omega P plus 1, goes to omega P plus 2, and so on to the top dimension by the de Rham differential. Well, the de Rham complex by the Poincare lemma is exact, but because we stupidly cut it at degree P, it's not exact at the first term. It has a kernel in the first term, and the kernel in the first term are the closed P-forms. So the stupidly truncated de Rham complex, which is the p step in the Hodge filtration on the de Rham complex, it's actually quasi-isomorphic to the closed P-forms on a smooth variety. And so when you're dealing with these fuzzy guys, the Stocky or derived spaces, that's the model that actually makes intrinsic sense, the stupidly truncated de Rham complex. So if you have Keller differentials on a derived space, then you can take the de Rham complex, so take wedge powers of Keller differentials and the de Rham differential, but now this is a double complex. And you can truncate it stupidly at degree P and take the total complex of that stupidly truncated guy, because it's, because the functions can have odd and even degrees. Now it's not a finite complex. It can go infinitely in the direction of the forms. So when you are taking the total complex, you need to take it with respect to you need to take it with respect to the product rather than the direct sum. But you totalize, you take the total complex, and you call these the closed P-forms. So it's the total complex of this double complex where one differential is the internal differential in the cotangent complex, in its wedge powers, and the other differential is the de Rham differential. And you can also shift that complex because it's a complex now. You can shift it by any number, any integer n, and that shift is just appearing in the total shift. And then you have a Hodge tower, which is the analog of the Hodge filtration. So this, this P truncation is the P step of the Hodge filtration, and then you have these closed forms, and you can shift them by anything you want, and you get a whole tower of complexes, and that's the analog of the Hodge filtration in this case. So if you want to say explicitly what a closed P-form is, so remember a closed P-form is going to be a cochain in that complex, the total complex of the double complex. You can say it explicitly, right? So the double complex, it has pieces which are, so the p to h power of the cotangent complex is a complex itself, and you're taking in that p to h power, you're taking some piece of homological degree k. So a closed P form is a collection of guys in those pieces. So they sit in p plus I to h power of the Derived complex, and they sit in homological degree n minus I. And it's a collection of infinitely many guys like that. And they have to be closed with respect to the differential in the double complex, which is the sum of the two differentials. So that means that the Derived differential of the form should be minus the inner differential of the previous form, of the next form in the labeling. So that's the condition. So the condition is, so it's a whole collection of P forms, or forms of degree P plus I, but putting homological degree n minus I, so that the Derived differentials are killed by inner differentials. And so the underlying P form is just the guy that's omega 0, the guy that's in omega P and shifted by n. But everything else is what you need in order for that form to be closed, what closes the form. So we call it the key closing that form. And so that's the extra data. You need to give yourself these extra pieces in order to say what the closed form is. And it is an extra piece of data. It's not just the underlying omega 0 guy, but it's all of those higher guys that satisfy these equations. And in fact, this is exactly Rouxy's derived complex. If you look at forms of degree 0, you can always truncate at the 0 p's. So you have a map from n-shifted closed P forms to n-shifted P forms, which are just elements in the P to H power of the cotangent complex. And if you look at co-cycles rather than co-chains, so global sections or global cohomologies, then an n-shifted, the co-cycle corresponding to an n-shifted closed P form goes to a degree n cohomology class with coefficients in the P power of the cotangent complex. And the fiber of that map is the complex of keys, which could be or trivial or non-trivial. But if it's non-trivial, then it's just extra data that tells you what the meaning of closeness is. And you need to keep track of that data. And so this is what's happening in the local situation, and you can glue that. You can use these P forms, n-shifted P forms, and closed n-shifted P forms as maps from affine derived spaces to complexes, and you take their limit, and you actually get complexes, global complexes of P forms or closed P forms shifted by n. And you have a map between them. And you can define a space of P forms or a complex of P forms, a space of closed P forms, a space of n-shifted P forms, a space of closed n-shifted P forms. And then the actual forms are just paths in those spaces, or connected components in those spaces, or degree 0 cohomologies in the corresponding complexes. And so let me just give you some examples so that you get a sense of what's going on. So if X was just a scheme or a space and it's smooth, if it's a manifold, then you won't get any negatively shifted forms. There are no negatively shifted forms. If it's affine, but derived maybe, then there are no positively shifted forms. And for a general guy, which is not affine and it's not a scheme, but it's a derived stack or a derived space, you can get shifted forms for arbitrary shifts. So the interesting thing is that if the scheme is proper, if you get a smooth manifold which is compact, then the keys are not there. The homotopy fiber, the complex of keys, the thing that closes the form, it's either empty or contractible. So for a smooth proper scheme, you don't really get any new information. What you would call a closed P-form is what you would call a closed P-form normally. For shifted forms, it's slightly different because we've used these truncated de Rham complexes, so it's going to be some forms in the steps in the Hodge filtration, but they're just going to be forms. There is no extra data in them. And you can define them in global terms always, as we proved, which, I mean, this is needed for computations, but you probably won't digest the utility of this right now. I just wanted to throw the statement there. But so let me show you some examples. So if you have an affine scheme which is smooth and has no extra structure, no stackiness, nothing derived, then the closed and shifted P-forms are 0 if n is negative. If n is 0, they're just the closed P-forms on that affine scheme. And if n is bigger than 0, they are the n plus pth de Rham cohomology of the affine scheme, cocycles of degree n plus p on our affine scheme. There is one tricky thing that one has to pay attention to, has to remember, which is that if you write forms by their local representation in terms of differentials, that representation may have different meanings. So if you take X to be C star, the punctured plane, punctured complex line, then the Z over Z, you can think about it as one form, which is closed and is not shifted. But you can also think about it as a 0 form, which is closed and it's one shifted. Because of this de Rham cohomology appearing for higher shifts. So just writing the Z over Z could be confusing in this setting. You really need to specify which the Z over Z you mean. Do you mean the unshifted one form, or do you mean some shifted form but of different homological degree, namely 0?
Hi, Tony. Just a quick question. The second one would have to be the class of dz over z, right?
Yeah, it's got to be the class of dz.
Whereas the first one is not the class.
Where the first one is, well, it's still the class because, you know, we are on an affine guy. So this is really H0 of omega p class.
Right.
But it's not the de Rham cohomology class of that. Yeah.
Okay, thanks.
Yeah. Okay, and if you have a smooth proper scheme, then the n-shifted closed P-forms are just a step in the Hodge filtration, and in fact, you can look at the higher cohomologies of this complex, and there are still steps in the Hodge filtration, just in different homology groups. If you do a stack, which is non-derived, and you represent the stack by a simplicial scheme, then you have a Czech interpretation of the forms on that. You can write the Czech complex for that simplicial scheme, and the P forms shifted by n are just the Czech homologies of that double complex. So in particular, if you have the classifying stack of a group, the n-shifted P forms are 0 if n is not P, and are the invariant polynomials on the Lie algebra if n is P. And something that's going to come handy very soon when we talk about symplectic structures, if you look at the closed P forms on BG, which are shifted by n, then they're 0 if n is odd, and they're the degree P invariant polynomials if n is even, for O even n. Here is another example which may be familiar and may be also instructive. If you take a derived space, which is the 0 locus of a section of a vector bundle. So you see, if you take a section in a vector bundle, if the section is not regular, the zero locus of that section will have a natural derived structure because it's a derived intersection. It's a non-transverse intersection between that section and the zero section. So its function theory has this extra nilpotence. The cotangent complex, you can write it in terms of this double complex on the total space of the bundle, this two terms complex on the total space of the bundle that I wrote before for any derived intersection. But it actually has a smaller model here, which is useful, and it's what one does in practice. So the cotangent complex of the zero locus of a non-transversal section in a vector bundle, it's a complex on the zero locus. So the xz is the underlying just zero locus. And the cotangent complex of the derived zero locus is a complex on that underlying zero locus. It has two terms. The first term is the dual of the vector bundle restricted to the zeros of the section. The second term is the cotangent bundle of the manifold restricted to the zeros of the section. They sit in homological degrees -1 and 0. And the map between them, it's, so, you need to take a section in the dual bundle and produce a one form. And the way you do it is you take a connection on the bundle, you differentiate the section that's given, that gives you a one form with values in the bundle, and you contract with your element in the dual bundle. So that gives you a map between the dual bundle and the one forms, which tells you that this is a well-defined complex, and that's the cotangent complex. You have to be a little bit careful here because the connection, it has to be algebraic. It may not exist. Right? Not every vector bundle has an algebraic connection, but every vector bundle has an algebraic connection locally on affine opens. And so you can take that algebraic connection, you can take the derivative of the section and contract with it. And the point is that this does not depend on the choice of a connection once you restrict it to the zero locus of the section. It's very easy to see if you write the difference of two connections and differentiate the section, you'll see that you get a multiple of the section in the difference. And when you restrict to the zero locus of the section, that disappears. So this guy really, so this model of the complex really is a good model on the whole zero locus. And if you choose your connection, really choose your connection locally, so locally you can resolve this two-term complex by a double complex, which is really the analog of the Kouzou complex that gives you the function theory on the zero locus of the section. You can use this to understand two forms. And since we'll be talking about two forms in symplectic structures, let me just say it. So you take the second wedge power of the complex, it gets resolved by the second wedge power of the Kouzou complex. And now you can say what are two forms of degree -1, they correspond to these two pieces in the Kouzou complex. Two sections in the dual bundle tensor, two forms on the base, and sections in the dual bundle tensor, one forms in the base. They sit in different homological degrees. And the Derived differential that sends one forms to two forms is the sum of our connection and the Kouzou contraction that contracts skew-symmetric sections with symmetric sections in the dual bundle. And you can actually say what a closed two form is of degree -1 in these terms. And that's something that actually was somehow the prehistory of this whole theory of closed forms, which was discovered by Kai Berendt. So if E is the cotangent bundle itself, and our section happens to be a one form then a two form of degree -1 on the zero locus of that one form is a pair of elements. One is in omega-1 check tensor with omega-2, so this is just the tangent bundle. And the other is in omega-1 check tensor omega-1, which is the homomorphisms from the cotangent bundle to the cotangent bundle. And it has to satisfy that the commutator of the connection with the contraction of the section applied to this phi guy is the contraction of alpha with the section. And if you take phi to be the identity and you choose your connection locally to be torsion free, so that the derivative of the identity is 0, then this says that this commutator acting on the identity is the derivative of the section, which means that this one form here, alpha, together with the identity, is a two-form, closed two-form of degree -1, if and only if D of S is the contraction of the section with alpha. So this is what's called an almost closed one form. So it's not a closed one form, but it's a one form whose derivative vanishes on the zero locus of the section. So this is how Berendt actually discovered this story, and he went on and used those almost closed one forms to construct perfect obstruction theories, symmetric perfect obstruction theories. But in this context, they're nothing but -1 shifted closed two forms. Okay, sorry. So this is this is the end of my introduction of this derived geometry. And now let me talk about the symplectic forms. So if you have one of these derived stacks, which are smooth, locally affine presentation, then an n-shifted two form is just an element in the second wedge power of the cotangent complex shifted by n. It's non-degenerate if, when you contract with this guy, you get a map from the tangent to the shifted cotangent bundle, cotangent complex, which is a quasi-isomorphism. And it's symplectic if it's lifted to a closed n-shifted two form. So a symplectic n-shifted form is a closed n-shifted two form whose underlying form is non-degenerate in this sense. That it gives you its contraction with it gives you a quasi-isomorphism between the tangent and the cotangent complex shifted by n. Okay. And this non-degeneracy, it's actually very important because it identifies the two new pieces of information in the geometry. So if you have stackiness or extra nilpotence derived structure on your space, this non-degeneracy identifies the Stocky directions in the cotangent complex with the derived directions in the cotangent complex. Right? The cotangent complex has pieces that are responsible for the extra nilpotence. They sit in negative degrees. It has pieces that are responsible for the extra automorphisms. They sit in positive degrees. And the symplectic form actually identifies these positive guys with these negative guys. So you actually get some way of interpreting symmetries as derived functions and the other way around by using the symplectic structure. So for the classifying stack of a group, we said what the closed two forms are. They're just the invariant, G-invariant quadratic polynomials on the Lie algebra, and they will be symplectic if they're non-degenerate. And so you get immediately a symplectic two-shifted two form on BG, which is given by a killing form on your Lie algebra. So if your group is reductive, you get immediately a two-shifted symplectic form on BG, which is given by the killing form. So that gives you a supply of two-shifted symplectic guys. Of course, you get a good supply of zero-shifted symplectic guys, which are just symplectic manifolds. But you also get n-shifted symplectic guys if you take cotangent bundles. So if you take the cotangent bundle of a manifold, it's zero-shifted symplectic. But if you place the fiber of the cotangent bundle in homological degree -n, so this is the spectrum of the graded algebra, which is the symmetric algebra of the tangent complex shifted by -n. then this carries the tautological symplectic form, and now it's n-shifted. So by shifting the fiber of a cotangent bundle, you get a lot of n-shifted forms. So those are the ones, the ones on the classifying spaces, the usual symplectic guys, and the shifted cotangent bundles. Those are the ones that you get by not doing any work, by just using information that we have classically. And now there are two constructions that can take known shifted symplectic structures and produce new ones. The first one is an analog of a theorem of Alexandrov, Kontsevich, Schwarz, and Zaboronsky in local quantum field theory. And geometrically, it says the following thing: if you have any n-shifted symplectic stack, and you have a derived stack X, which is oriented, so it looks like a Calabi-Yau. It has an orientation on the cochain algebra of the function theory. It has a functional on the cochain algebra of the function theory with values in the constants placed in homological degree D, so that, which is non-degenerate in some Poincare duality sense or Serre duality sense. So it looks like a Calabi-Yau structure. So any such guy gives now rise to a new symplectic guy, because you can look at the moduli space of maps from the oriented guy to the symplectic guy. And as I said, in all normal examples, this is going to be an arting derived algebraic stacks of locally affine presentations. So it's going to be smooth by this hidden smoothness philosophy. And it carries a natural now symplectic structure that depends on the symplectic structure on the target and the orientation on the source. But it's with a different shift. It's n minus d shifted symplectic.
Tony, in their story, they mapped, what did they map? Riemann surface to...
No, they mapped a general formal space.
Yeah, you consider a space of map to something symplectic,
yeah,
so you have a
in
pairing.
their story, X is the space of fields in some
yeah, and you integrate over the volume on X. Yeah. Okay.
Yeah,
mm-hmm.
but that space of fields, they only looked at it formally at a point, but kept the orientation and then mapped it to some Poisson algebra of observables, and that's what they had.
Mm-hmm.
So one thing I wanted to point out is that the source here, so these Calabi-Yau guys, they could be actually compact-oriented topological manifolds. A compact-oriented topological manifold of dimension D that's viewed as a derived stack, as a constant derived stack over the site of schemes, it's a Calabi-Yau in this sense. It's a Calabi-Yau of dimension D. So the orientation gives you a Calabi-Yau structure of dimension D. So if you look at maps from that to anything symplectic, then you get something symplectic again. And that's one way to bring the symplectic structure on D-branes.
What does O compact mean?
O compact means that so it's that non-degeneracy condition that I didn't explain. So it means, first of all, that the structure sheaf is a compact object in the category of quasi-coherent sheaves on X. And then it means that this linear map that I'm specifying here satisfies a non-degeneracy with respect to Serre duality. That's what O compact means. So I mean, you can go. So this is in our paper from about 10 years ago with Bertrand, Gabriele, and Michel, where we introduced shifted symplectic structures. So you can go there and see the definitions. It's just some finiteness condition, basically. Okay, so you can also have constructions of symplectic structures in a different way by doing an Lagrangian intersection. So if you have an n-shifted guy, you can talk about the Lagrangian in it. Now you have extra freedom because the Lagrangian is not really a sub-manifold, because this is not a manifold, it's just a derived stack, but it's something mapping to Y. So if you have a map from another derived stack to Y, you can say what an isotropic or a Lagrangian structure on such a map is. So an isotropic structure is, well, it's again something like, you need to take the symplectic structure, pull it back, and you need to say it's zero. But because the symplectic form was this closed form, and being closed was that extra information, what it really means is that when you pull back the closed form, it's not zero, it's some cochain, it has this extra higher order terms, it's some cocycle, but it's not zero, it's a co-boundary. So you need to specify some homotopy between this closed form to zero. So that's the isotropic structure. And then you can say what it means for it to be non-degenerate. It's in the usual way. It means that, so Lagrangian, it means that when you contract with this co-boundary, the relative tangent complex for the map, so that's like the normal bundle for the map, you get to the cotangent complex of the source shifted by n-1, you need this to be a quasi-isomorphism. So that's the usual way of which we are saying on isotropic structure. A Lagrangian submanifold is an isotropic submanifold for which the contraction with the symplectic form gives you an isomorphism between the normal bundle and the cotangent bundle. So this is what it looks like in this shifted context. And a usual Lagrangian in an unshifted symplectic guy it's a shifted Lagrangian in this sense. But it's also interesting to notice that Lagrangian structures and symplectic structures are actually on an equal footing, because you can take a point with the zero symplectic structure, but putting homological degree -n-1, and then a Lagrangian structure on a map from a space to the point will be just an n-shifted symplectic structure. So you can describe Lagrangian structures first and define the n-shifted symplectic structures in their term, in terms of them, or you can do it the other way around. And sometimes it's useful, but anyway, it's interesting and useful to notice this. And the Lagrangian intersection theorem tells you that if you have two Lagrangians in an n-shifted symplectic stack and you intersect them, then that intersection naturally carries an n-1 shifted symplectic structure. So intersecting two Lagrangians in an n-shifted symplectic guy gives you an n-1 shifted symplectic guy. So these two theorems that actually give you a large supply of new symplectic spaces, and in fact tell you how to construct symplectic structures, shifted symplectic structures on moduli spaces. Sorry, I'm running out of time, so I hope people are not, I'll need probably about 20 more minutes to get to an interesting new statement. How are people doing?
You can go over that time, it's okay. Those who cannot, they can.
Don't be surprised, I'll be going on for a while, at least for 20 minutes. Okay. So an interesting special case of this Lagrangian intersection is the derived critical locus of a function. So if you have a smooth function on a space Y, then the derivative of that function gives you a section in the cotangent bundle, and you have the zero section, and you can intersect those, and you get the critical locus of the function. But if you intersect them in the derived sense, you get the derived critical locus. So that's the guy for which the function theory, so it's the critical locus of the function, but equipped with the function theory in which you have nilpotents, which remember about the higher normal derivatives of the function along the zero locus. And this guy is now symplectic because it's the intersection of two Lagrangians. These both are Lagrangian sections in the cotangent bundle, and it's a -1 shifted symplectic guy. So the derived critical locus of a function always carries a -1 shifted symplectic structure. And the derived critical locus of a shifted function, say an n-shifted function, will carry n-1 shifted symplectic structure. So that it's actually a useful information. In fact, it's an information that that physicists like to keep track of. So in physics, Y will be some space of fields, F will be some action functional on this space of fields, the critical locus will be your space of physical fields. But in perturbation theory, you don't want to just keep track of the critical locus, especially say in BRST quantization, you want to keep track not just of the critical locus, but of the physical fields, but you want to remember the normal derivatives of your action functional to the physical fields in the ambient off-shell space. And this is exactly what this derived critical locus achieves. And there is some duality between those normal derivatives and the symmetries of the theory. And that's the -1 shifted symplectic structure that you want to keep track of. Okay, so here I'm approaching my somehow ultimate goal for the discussion. What are the local models of these shifted symplectic geometries? So in classical symplectic geometry, locally all symplectic manifolds look the same. Right? There is the Derived theorem, which says that if we are, say, on a usual differentiable manifold, or if we are on an algebraic manifold or in an analytic manifold, then if I have a manifold which is symplectic and I have a Lagrangian, then locally this pair always looks the same. It looks like the cotangent bundle of the Lagrangian as a symplectic manifold. It's locally isomorphic to the cotangent bundle of the Lagrangian. That's the Derived theorem. And you know, it comes in various degrees of generality. So in the differentiable context, it's really along the whole Lagrangian locally near the Lagrangian. In the analytic setting, it's locally formally, in the algebraic setting, it's locally formally or et al. And in the analytic setting, it's locally analytically. But the point is that locally every symplectic geometry on a smooth guy is modeled by a cotangent bundle. It is really the cotangent bundle of some Lagrangian. And that is what you would like to understand in this setting. Is that true for derived stacks? And the immediate observation is that it's not. It's not true that locally everything is a cotangent bundle or a shifted cotangent bundle. Because derived critical loci, so shifted cotangent bundles, by the way, are derived critical loci. They're derived critical loci of the zero function or of a constant function where the derivative is zero. So shifted cotangent bundles are derived critical loci of shifted functions, constant shifted functions. But if you take a non-constant shifted function and you take the derived critical locus, that's not isomorphic locally to a cotangent bundle. That's very easy to check. And so the natural guess will be that if you want local models, you can't really use shifted cotangent bundles. You have to use derived critical loci for shifted functions. And that's the Derived theorem that was proven by Bembasad, Bussy, and Joyce. It says that if you have a derived Deligne-Mumford stack and you have an n-shifted symplectic structure which is non-negatively shifted, then it's actually locally exact. And et al. Locally, that stack is isomorphic, well, not to a shifted cotangent bundle, but to a derived critical locus on some space. Derived critical locus for a shifted function. So not a function, but a degree n cohomology, degree n cocycle with coefficients in functions, n+1. And so the point is that locally every shifted symplectic geometry is given by a potential. It's given as the derived critical locus of a shifted potential. And the question I would like to address is, when is it given globally? as the derived critical locus of a potential. And the reason that's an important question is because in physics, always spaces of fields are given globally as derived critical loci or critical loci of action functionals, modulo symmetry group.
What
So
about Chern-Simons, Tony, which is not well defined globally? It's well defined only when you lift it to the universal cover.
Yeah, so I'll come to that. In fact, you can define it globally, but you just need to define it formally. But you know, the Chern-Simons functional actually gives you a global realization of the moduli of flat bundles on a three manifold. It's just infinite dimensional, but it gives you a global realization as a derived critical locus, or as a critical locus, or even the moduli of derived moduli of flat bundles as a critical locus. Just the problem is that really the construction is formal near connection. But I'll come to that in a moment.
Could I just ask why in the last couple of slides did you change from Artin to Dilling-Mumford?
Yeah, so there is a tricky point about the Derived theorem that their proof just doesn't work if you have affine stabilizers, non-finite ones. You do expect to have a version of the Derived theorem for Artin stacks, but their proof just doesn't work. And so some of the stuff I'm going to say is going to tell you how to do it for Artin stacks too. So the punchline is that you'd have some Derived statement. Right now it works, say, for derived spaces or derived Dilling-Mumford stacks. Doesn't quite work for the Artin stacks, but you expect it to work. Just we don't know how to prove it, or maybe properly formulate it. But it's saying that, you know, there are local models for geometry that come from this derived critical loci of potentials. And the question is, how do we understand those potentials, and how do we understand when they exist globally? So I'm going to tell you both answers. So the point is that they always exist if you have an isotropic foliation on your symplectic guy. And in fact, the potential is really something that comes from an isotropic foliation. So here is the statement: take a derived stack locally finite presentation. Suppose that you have an n-shifted symplectic form, and assume that it's exact. Right? I mean, this derived critical loci are always exact. So if you want to have a global potential, the symplectic form has to be exact, or otherwise you have to do it locally, so that it's locally exact. But so suppose that you have a derived stack which is locally finite presentation, an n-shifted symplectic form which is globally exact. So it has a zero class in the Derived homology. If the symplectic stack is equipped with a foliation which is isotropic for the symplectic form, then you can quotient the stack by that foliation, and you get a geometric object on which there is a function, n+1 shifted function, and the derived critical locus of that n+1 shifted function will be n-shifted symplectic, and there is a natural map from your x to that derived critical locus, and that map is symplectic. So if you pull back the symplectic form on the derived critical locus, you'll get the symplectic form on the original guy. And if the foliation is actually Lagrangian, that map from the original guy to the derived critical locus is actually a tau. So not only is the map symplectic, but it really gives you a local model for your symplectic structure. So this is the punchline. The punchline is that if you have an exact symplectic form, and if you have a Lagrangian, well, at least a isotropic foliation, but if it even a Lagrangian foliation for that form, then your symplectic structure actually comes from a potential, global potential. And if it's, you know, if you're doing this locally, then you would want your foliation to exist locally, and foliations always exist locally. So you can actually prove the Bembasad-Bussy, Braff, and Joyce theorem in the Artin-Stack situation this way locally by just noticing that Lagrangian foliations always exist locally.
What is a Lagrangian or even isotropic foliation in the derived sense?
Well, it is, you know, we said what Lagrangian is or what isotropic is, so it is the same thing. So rather than mapping a space now, you're mapping a complex to the tangent complex. So it's just some complex on your X with a map to the tangent complex so that the map is isotropic for the given symplectic form. So that complex, of course, has to be a foliation. So it has to be a Lie algebroid. So it has to be a complex of DG Lie algebras mapping to your tangent complex. And the map has to be a map of DG Lie algebras. And the map has to have the property that the pullback of the symplectic form is equipped with a homotopy to zero or with a co-boundary. And it's Lagrangian if the contraction of that guy with the symplectic with that co-boundary is giving an isomorphism with its dual, the dual Lie algebroid. So it is exactly the same thing that I did in the geometric case, but done with foliations. And you know, if your guy was not derived, if the tangent complex was just a vector bundle, then it would be just a Lie algebroid, which happens to be isotropic or Lagrangian. But this is the punchline, and let me just say that this condition about the form being exact, it's actually automatically satisfied in the negatively shifted case. Every negatively shifted form is globally exact for some Hodge theoretic reasons. And so this recovers this theorem of Bembasad, Braff, Bussy, and Joyce, and also extend it slightly to the Artin context. But what I want to take out from this is I want to talk about actually constructing these realizations of moduli as critical loci of potentials in interesting situations. And in order to construct them, you have to, in fact, you know, the theorem is constructive. If you have the foliation, you can actually construct the function. So in order to construct them, I want to produce those foliations in interesting geometric situations. And so I have a lot of examples actually of these global realizations, which you can read through in the slides, but I'm not going to go over them. So I have examples corresponding to derived critical loci. I have examples corresponding. So derived critical loci, of course, examples of that. So this is just reversing the derived critical loci construction. But then there are interesting examples for twisted cotangent bundles and for integrable systems. I'm not going to go over those. I want to show you two new examples that are not covered by stuff that we understood before with shifts. So in particular, one of those will give you an extension of the Chern-Simons functional construction to manifolds of higher dimension. And the other is going to be something from non-abelian Hodge theory. So I want to show you those two constructions and examples. So I'm going to skip the examples that are shifts of familiar things. And I'm just going to talk about the higher Chern-Simons functionals. So suppose we have a compact-oriented manifold of odd dimension and bigger than 1. So dimension 2k plus 1. So for 3 manifolds, so what our goal here is we want to understand the moduli of local systems of such a manifold. And we want to understand it as a symplectic guy, and we want to understand it as a symplectic guy which is given as the critical locus of a potential somewhere. And that potential will be the Chern-Simons function that realizes that moduli space. So for 3 manifolds, it will be just the usual Chern-Simons functional, or some globalization of the usual Chern-Simons function. But for higher dimensional manifolds, it's going to be something new. So suppose that we have one of those odd-dimensional manifolds. Now to construct the potential realization of the moduli of local systems, I'm going to choose a more small function. So it's going to be a function, differentiable function on M, which is Morse and it's self-indexing. So if it has a critical point, then the value of that critical point will be equal to its index. So by Smell theory, we know that these more Smell functions always exist. So I'm going to choose one of them. Now I have a bunch of critical points that are labeled by, they go from the dimension to 0. And I'm going to choose a regular value which sits between in the middle interval, right? So because the dimension is odd, there is a middle interval that sits between critical value 1, k and k plus 1. And I'm going to choose a regular value there. I'm calling it C. Now take the pre-image of the half ray that goes from negative infinity to that regular value C. That's a submanifold in M with boundary. And I'm calling it M plus. And the inclusion from M plus in M, it's a homotopy equivalence on the k-dimensional skeleton of M, because mu is a Morse Smell function. Now take a complex reductive group G, and you look at G local systems on the manifold M. So locally constant principal G bundles on M. So this thing is an algebraic moduli space. It's an algebraic, you can write it as an affine algebraic variety, but you can also understand it as a derived algebraic stack, parameterizing these locally constant principal G bundles on the manifold M. And it's a mapping stack from M to BG because M is oriented. This induces a symplectic structure, which is 2 minus D shifted symplectic. BG is 2 shifted symplectic. M is oriented with orientation of dimension D, so we get a 2 minus D shifted symplectic structure on the moduli stack of local systems, which I'm calling Bun-G M. And if k is bigger than or equal to 1, then 2 minus D is negative, so this actual symplectic structure is exact. So I can ask, when is that stack actually the critical locus of a global potential as a symplectic stack? And the answer is always, and because there is a natural foliation that corresponds to our manifold M plus, to our half of the handle body decomposition of M. So you look at local systems on M, you can restrict them to local systems on M plus. That gives you a map of moduli spaces. And the tangential, the relative tangent complex to that map is a foliation on Bun-G M, the tangential foliation. And that foliation is actually isotropic. It has a natural isotropic structure. It only depends on the orientation data on M. And the symplectic structure, symplectic form on BG. So you can quotient by that foliation, and you get some formal stack, which is a quotient of your stack of local systems. On that stack, you get a shifted function, 2 minus 2k shifted function. And the map from the stack of local systems to that critical locus, it's a symplectic map. It's kind of hard, so we haven't actually proven that that foliation is Lagrangian, even though I expect it to be Lagrangian always. We only prove that the structure that we constructed is isotropic. We can prove that it's Lagrangian under some topological conditions on M. So for example, if M is a k pi 1, we can prove it. we can prove it if M is simply connected. We can prove it under some conditions on the Postnikov tower of M. So there, you need some Postnikov classes to vanish to actually cheaply prove that the thing is Lagrangian. In general, I expect it always to be Lagrangian, but we haven't proven it. But it's certainly isotropic, and the map is symplectic. So it realizes, so this guy, this F, which corresponds to this foliation, to that isotropic structure, that is the higher dimensional Chern-Simons functional. It's defined on some formal stack, but it's well defined. Okay, I exhausted my 20 minutes, so maybe I am going to stop here. So there was another example from non-abelian Hodge theory, which I'm not going to review, and you can look at it in the slides. But maybe I'm going to stop here and let you ask some questions.
Okay, thank you, Tony. Questions? Yeah, I have a question. In case if your G, whatever is a general linear group, I mean, it's a question about categorification. So yes, you know that this, the potential on the stack of objects, it's a consequence of some additional structure in your category, like for -1 shifted, it's like Calabi-Yau, like 3 Calabi-Yau. This 2 minus D is equal -1. So what about existence of a global potential?
Well, global again, in the sense that there is some formal stack on which it exists. I mean, I expect it to be true. So, you know, if you have a smooth compact Calabi-Yau category of dimension D, and you look at the moduli stack of objects in that, of compact objects in that, I expect, and this is shifted symplectic. It's 2 minus D shifted symplectic. And I expect again that 2 minus D shifted symplectic structure is induced from some global shifted potential. It realizes the moduli stack as a global critical locus of some global shifted potential, and the symplectic structure is the same. So you need to find some natural Lagrangian foliation or isotropic foliation on the moduli stack. But I do not have a categorical construction of that foliation. In fact, you know, you could ask the same question even before categorification. So I did local systems on an odd dimensional manifold. You can do local systems, sorry, not local systems, you can do moduli of perfect complexes or coherent sheaves on an odd dimensional projective Calabi-Yau. So those are also shifted symplectic. And, you know, for 3 Calabi-Yau threefolds, you have the holomorphic Chern-Simons functional, which realizes them as a critical locus. And you can ask whether that makes sense in general, or whether the holomorphic Chern-Simons functional corresponds to some foliation on the moduli. And I do not know the answer to that question. I mean, I expect it to be true. I expect that there is a foliation, so there is some analog of this more small construction. But I don't know how to do it. So we actually thought about it a little bit for the threefolds, because, you know, you can try to degenerate your Calabi-Yau threefold to a union of 2 quasi-Fanos intersecting at the Calabi-Yau surface. So that's the analog of this handle-body decomposition. And you can try to restrict to one of them and try to get your foliation that way. But there is a problem with the specialization in the degeneration, which it's kind of hard. I think we solved it. We can define the specialization in the degeneration, but we couldn't prove that the tangential foliation for the restriction of the one of the Fano components is isotropic. We couldn't construct the isotropic structure. Maybe we weren't clever enough. But you know, this is already geometric, not categorical. And how would you do this categorically? I don't know.
Yeah, I have kind of, sorry, two more questions. So one about this Chern-Simons story. I remember that like when we wrote that paper with Maxim about Donaldson-Thomas motivic DT invariance, it's a very first paper. We have some proposal for higher dimensional analogs of Chern-Simons, which are related to odd dimensional Calabi-Yau algebras, but again, odd dimensional, like in your story. On the other hand, people like Joyce, they write some invariants for like 4-dimensional Calabi-Yau. What to do with even dimensional things?
Yeah, no, you can. There is an extra layer of complication. I mean, you can actually prove an analog of this theorem, which we haven't, but it's clear what it should be for even dimensional ones. Just the problem is that there is an obstruction to having a Lagrangian foliation on local systems or perfect complexes on even dimensional guys, even dimensional Calabi-Yaus. It's a signature L class. So you need to kill that obstruction, otherwise you have no chance. It's not enough to have a negatively shifted form. You also need that obstruction to vanish, otherwise you have no chance of actually constructing the potential. And so what you really have to do, so this obstruction is some quadratic form on the shifted tangent bundle, and you need to pass to the derived critical locus of that quadratic form. Replace your stack of local systems or stack of perfect complexes.
Yeah, that makes perfect sense. If you, for example, look for this Nekrasov story when he works with like C4, like the simplest possible Calabi-Yau, in order to define, well-define the virtual number of instantons, he needs some structure, some splitting of quadratic form, which kind of...
Yeah, that, I mean, you know, if you look at what Joyce and Kao and Lung and all those people do, they also do that, right? I mean, they look at the middle cohomology of the endomorphism algebra, which describes your cotangent complex, and there is a pairing now on the middle cohomology, and they need to choose. So that pairing is
one half of it, yeah, like polarize it.
Yeah, exactly. They need to choose an isotropic structure for that guy. So that's the same as passing to the derived critical locus. And on that you would expect a global potential. And the same thing should work here, but again, you know, this L class is always there. The signature L class is always there in the even-dimensional case. And again, you need to find that foliation, and presumably this, at least in the topological context, this choice of handle-body composition should do it, but we haven't checked it. I mean, it may be a tricky thing in surgery theory because you would want your handle-body composition to somehow be adapted to the signature operator. So.
Okay, more questions? Mark.
I have a question.
Oh, sorry. Go ahead.
I have a question. So for the easy piece, for the critical locus of a regular function, the -1 shifted, what's the you know, easy example for the Lagrangian there? You mentioned the Lagrangian inside is -1 shifted.
Say it again. Just repeat the question.
If you have a D critical locus, like a -1 shifted. Right? And then what's the example of a Lagrangian?
Oh, you're saying what's the Lagrangian foliation for an actual potential? Yeah. So I didn't go over that, but I actually have slides.
You have an example there? Oh, sorry. Can I take a look?
You can go and see them. So so if you have a smooth guy and you have a potential, and this also works in the shifted case, and you take the derived critical locus, then you have a map from the derived critical locus to the smooth guy. And you can look at the relative tangent complex for this. So that's the foliation. That's the Lagrangian foliation. And you can actually construct the quotient. The quotient is the formal completion of the derived critical locus inside the ambient guy. And the potential is just the restriction of the given potential. The potential that you get from the foliation is just the restriction of the given potential. So this does reconstruct any given potential, you know, by taking the tangential foliation for the inclusion of the underived critical locus, the derived critical locus in the Andean sky. But in general, you need to find that. I mean, it's not.
I see. Okay, so this is an example for the
Yeah. So it's an example. Yeah.
Okay, thank you.
Okay, Marco, please.
So you have, in this case, the isotropic transversal foliation is given by an actual map. So you actually have the, in a way, it's almost as if you have the quotient map, and then you take the tangent.
Yeah.
Right. So I'm just wondering if you have some kind of integrability result. I mean, suppose that you really had only the distribution. If you only had the Lie algebroid, let's say.
No, but the Lie algebroid is already integrable, right? I mean,
yes. So suppose that you had the Lie algebroid and you knew that it was integrable in the sense of closure under brackets, right? Then you would need to integrate that and find the leaves in order to get your
but here, you see this quotient here, this quotient which is the leaf space, right? It's really only a formal algebraic star. It's not the actual leaf space. So in fact, if if you go and look at what I wrote there, if you have just a map between manifolds, right? You have one guy mapping to another, and you take the tangential foliation.
Yes.
Right, and you quotient by that. You don't get the base, right? What you get is you get the Derived stack for the fibers over the base. So it's really thickened by these formal directions, which are giving you the Derived theory, and that's where your global function lives. So it's not a very pleasant geometric object, right? It's this formal derived stack. But the advantage is that in this generality, you actually always have quotients by foliations. If you quotient, you can quotient actually any derived algebraic stack by a foliation, and you get a formal derived algebraic stack.
So just so that I understand, when you say a foliation, you mean the Lie theoretic infinitesimal data?
Yeah.
Not the actual.
I really mean the Lie algebroid. Yeah, I don't mean that algebroid is integrated to a groupoid in any way.
Okay.
So questions about isomonodromy, they do not appear. Yeah, like that something kind of is preserved along the leaves in the space of. Okay. All right. So more questions.
So this just now, Tony, you told me this is the Lagrangian. The example is in your paper. The example.
Say it again.
I mean, the Lagrangian example for the minus one shifted is written down in your paper, right?
Yes.
Okay, thank you. So which paper is the PTVV? Oh no, is the file?
You mean for the foliations or for
the foliations?
Yeah, no, the foliation papers, it's not written yet, but it's written here in the slides. I mean, so you can look at the slides.
Oh, it's the note. Is this example in your notes you send to the link?
Yeah.
But in the chat, Lina posted the link to the slides, so you can download it directly right now. There is a link in the chat to everyone. Okay, more questions?
There is a link, actually.
There is or there is no?
I don't think so.
I do see. Maybe it's the wrong one.
Yeah, there is one, but the people that arrive late cannot see it. I'll post it again.
Oh, thank you.
Post it again for any later arrival, so you don't see that right away. You won't see it.
Okay.
Hi, Tony. Good to see you.
Good to see you.
Okay. More questions?
Well, can I ask a ridiculous question?
Yes.
So I don't quite familiar with this subject, and you hear you giving the stack, and you have the shifted symplectic structure, because in the stack version, you could take a character of the group, and you could use the group to twist the structures. So, does this kind of question make sense in this setting?
you want to twist the notion of an invariant polynomial?
Yeah, I mean, including the possible symplectic structures as well.
You can do things like that. You know, you can look at symplectic structures with values in some vector bundle or in some vector space or in some complex. And so that's slightly different. It gives you some kind of a notion of a relative symplectic structure, but that's also useful. And you can do things like that, and you can actually construct those by similar constructions. But I'm not talking about them. I mean,
I know we didn't talk about that. I was thinking, so taking just the linear characters, that means corresponding to a non-bundle, which is twisted by the group, exactly. And everything can be tensored by that non-bundle.
Yeah, you can twist by that guy and look at the notion of a closed form or a symplectic form with values. And it gives you some interesting geometry too. In fact, there are some interesting constructions that I didn't cover of symplectic structures which use such twists. So there is one that was invented by Gaiotto in purely physics terms, and then was mathematically implemented by Ginzburg and Rosenblum, and it uses a degree 2 twist like that, and it's very interesting, and in fact doesn't fit in any other way of constructing symplectic structures because it uses this non-trivial twist. But yeah, I mean, the answer is yes, you can do it, but gives you slightly. You can use it to construct symplectic structures again.
By the way, Tony, your ground field has characteristic 0. Yeah, because there were some attempts to make sense.
Everything I did was in ground field in characteristic 0. If you want to do it in positive characteristic, you can do many things, but of course, you know, you have to use different models. You cannot use DG models for your function theory. You have to use simplicial rings, and so many things work. But many parts of the theory haven't been developed yet. But it's interesting though, because number theorists actually do look at these guys. They appear naturally in moduli spaces of Galois representations, and they carry interesting information. But I don't think all bits of the theory. So there are some papers on that subject. I don't think all bits of the theory have been developed.
Okay, thank you. Are there any questions? Okay, then let's thank Tony again for the wonderful talk. Thank you, Tony.
Bye.
Okay, and so we are disconnecting. That's the end of the meeting. Thank you very much.
It's good.